This video should help you if you are looking to make test corrections to your Chapter 6 test and do a retake with us after spring break. So we're going to go through each of the problems one by one, and the first problem gives you this little snippet of paper that was lost. Silly Carmen and Mario getting into an argument. And it says the x-intercept of the original graph is at 7, 0. And it's asking you to look at these three graphs, A, B, and C, and to decide which one of those could possibly be the inverse function of the one that is lost. And so based on the fact that we know that the x-intercept is at 7, 0, we know that the y-intercept of the inverse must be 0, 7. Remember, with the inverses, you always switch your x and your y. And so we know, given that, the only one of those three functions that could have a y-intercept at 0, 7 would be function A, and so that would have been the right choice for that one. So that's really all you had to do for problem 1. Let's move on to problem number 2. Problem number 2 gave you a bunch of different parts. It said to find the inverse for each of the following functions, and then to put it in y equals form, and gave you a little hint for letter B. Then it said to sketch the graph of each function and its inverse and to label them so you could tell. So my version of labeling is going to be to make the original function blue and the inverse purple. So I started on letter A. Let me go ahead and zoom in for you. I started letter A by graphing the original function, which is just a line at negative 3x minus 2. You can either do that by starting at your y-intercept and doing your slope of negative 3, or by graphing it in your calculator. Then in order to find the inverse, and you're going to notice on this video that this is my favorite way to find an inverse, you just switch your x and your y, and then you can solve it for y from there. So I rewrote this as x equals negative 3y minus 2, and now you're just going to see my different steps for finding the inverse. I just want to get y all by itself in this equation, and when I do that, I end up with y equals x plus 2 divided by negative 3. And so I can graph that inverse, and I can graph it like a line that is y equals negative 1/3 x minus 2/3. And so my y-intercept, you can see I just started to plot it, is at negative 2/3, and then I'm going to have a slope of negative 1/3. And so I graph that line, it's the purple one right there. And you can notice, if you liked the method that we learned in class about using the line y equals x as the line of symmetry, you can notice that if I put that line of symmetry between the two right at y equals x, they would be reflections of each other. Okay, you could also make a table of values for x and y, flip those, and then plot your new points. That's the third way we learned how to graph inverses. But I'm going to do it that way each time. Now I'm going to slide over to example B. And there was a hint that said, what domain restriction will we need to make B, the inverse of B, a function? And so we'll talk about that in just a little bit. But I started by graphing the g of x equals 3x squared minus 4, and that's a rough sketch of it as my blue parabola there. And then again, I switched my x and my y and solved this equation for y in order to find the inverse. And so I added 4 to both sides, divided by 3, and then took the square root. You'll notice that when I take the square root of both sides, I have to have plus or minus there. Okay, but if you did this by draw inverse on your calculator, if you typed it into your calculator, you'll notice that it only showed you the top half of this graph, and there's a reason for that. And that's because right now it doesn't pass the vertical line test. It's not a function. And so we have to restrict the domain of our original function so that when we draw the inverse, it is a function. And the way we do that is this. You find the middle of that blue parabola, and that happens to be on the line x equals 0. And that's the point at which when I flip it, all of these vertical lines cause me to fail the vertical line test on that purple parabola. And so I can only use one side of the blue parabola. Either I can use the right side, and my domain would be all numbers greater than 0, or I could use the left side, and it would be all numbers less than 0. Okay? And so I would have to pick that domain. If I picked greater than 0, it would look like just the top half of the purple parabola. If I picked less than 0, it would look like the bottom half of the parabola. So that's how you do that one. That's what that hint meant. Alright, we're going to look at this exponential function in letter C. And the graph of h of x equals 4 to the x power is an exponential growth function that goes through the point 0, 1. Now in order to find the inverse, you've got to switch your x and y again. and then change it so it's in log form. Okay, so it'll turn into y equals log base 4 of x when I use my little rule to convert it. And you can type that into your calculator, or you can just learn what we talked about with our toolkits and parent functions to know that the graph of that looks like that. Remember, every log function has an x-intercept at 1, 0, so you always need to go through that point. Unless, of course, we transform it, which we'll talk about later. Okay, so that's all you need to do for that one. Now, letter C again, which is actually D, is a little tricky, because if you look at it, this is what our original graph looks like. Then when I solve it for the inverse, I'm going to switch x and y. And I can multiply both sides by y, and then multiply or divide both sides by x in order to solve it for y. And I actually end up with the exact same inverse when I do that. So you would only have one graph. It is the same whether I'm talking about the original function or the inverse. Okay, and those are what all of the graphs and equations look like for problem number 2. Feel free to copy it or to pause the video and look back at that if you need to. I'm going to move on. Alright, problem number 3 asked us if the inverse of each of these functions is also a function. So the way that I dealt with A was I took that table of values and graphed it exactly as it is. Now, if you look at that V that I made, if I turn that and I switch x and y, I flip it on its side, it's not going to pass the vertical line test. I'll have 2 points that go through the x value of 2 and 2 points that go through the x value of 4, and so that is not going to be a function when I graph the inverse. If you look at letter B, if I were to flip the x and y there and graph that, it would be a function. It would pass the vertical line test. And in order to figure out if C's inverse graph would be a function or not, I graphed this log function, the transform of it. And so it's a log function that goes through the x-intercept of 6, 0, since it shifted 5 units to the right of where it normally is. And if you graphed the inverse of a log function, that exponential function would also be a function. So that one works as well. Okay, moving on. It asked me to prove if these two functions were inverses of each other. Now, in order to do that, I'm just going to start with f of x, and I'm going to find its inverse. If it happens to be g of x, then I'll know that they're inverses of each other. There are many different ways you could do this. We talked about how you could do this with composition functions. We talked about, you could just have graphed them, but I wanted to see it algebraically like this, and so I just switched my x and y in f of x, and we're going to see what happens. So I add 5 to both sides, then I'm going to take the cubed root, and then I'm going to subtract 4. And what you notice when you do that is that you end up, when you solve for y, with the exact same function that we have in g of x. So, of course, they sure are inverses of each other. Drew a little smiley face because that makes me happy. I'm done with this problem. Notice that they're the same, and we can move on. Alright, now I'm going to use a similar strategy for figuring out which two of these 3 functions are inverses of each other. And so I'm going to start with that first one, and I'm going to see what its inverse is. If it matches with g or h, then I know that I'm done. Okay, so I'm going to take this x, or f of x, I switched x and y, and I'm going to solve for y. So algebraically, I multiply by 5 on both sides, then I subtract 4, and then I divide by 5. Sadly, that function does not match either of the ones g or h, and so I have to try another one. Hopefully g and h are inverses of each other, otherwise we're having a bad time. So I'll check g, and when I do that, I switch my x and y again, multiply by 2 on each side, add 4 to both sides, and divide by 5, and yay, happy face, that's the same function as h, and so g and h must be inverses of each other. So I know that I'm done. You could check it the other way too, to double check. Make sure when you find the inverse of h that it is g. It should work both ways, but you don't need to do that, so I can move on. Alright, this problem asked us to switch between logarithms and exponents. Now, it did not want you to find the inverse of these log functions, it just wanted you to switch forms. And so what I used, and I wrote on the top of the paper here, was the definition to switch between logs and exponential function. And so all I can do is I can take that, and I can use all the patterns that we talked about to try and rewrite these in exponential form. So I'm just going to fly through these because you should have been able to go through them really quick on your test. And so when I rewrite them, just using that definition, for letter A, I end up with 5 to the y power equals x. For B, I end up with x to the 5th power equals y. For C, I end up with y to the 5th power equals x. Now you'll notice on all of those, I take the base of my log function, I raise it to what's on the other side of the equal sign, and it equals whatever was next to the base in my original log side. Okay, and now in part 2, we gotta take it and go backwards. So we're gonna change from the right side of this definition, and we're gonna move it over to the log side. Okay, so when I do that with letter A, I end up with y equals log base x of 5. With letter B, I end up with y minus 2 equals log base 8 of 5. And then in order to make it in y equals form, I have to add 2 to both sides before I'm done. And then you'll notice that letter C, you don't have to use a log. All you have to do is take the square root of both sides. And don't forget that when you take the square root in an equation, you end up with plus or minus. So you get y equals plus or minus the square root of x. If you need to pause for a minute to make sure you understand that definition, go ahead and do that. Alright, now so for these problems, it's using the same idea. You have to understand the definition of switching between logarithms and exponential functions. But basically we want to solve and we want to figure out what x is. So I'll show you what I did for each of these steps. And I raised 3 to the 5th power equals x, and then simplifying that just tells me that my x is 243. In letter B, I take x to the 4th power, and I should get 16. And you could just guess and check, or you could take the 4th root of 16, and either way, you would get x equals 2. Letter C says 4 to the x power would be 64, and you know based on that x has to be 3, 4 to the 3rd power of 64. Letter D, it's going to take me one extra step, and I say 3 squared equals x plus 3. I know 3 squared is 9, and so I know 9 is x plus 3. I subtract 3 from both sides, and I get x equals 6. In letter E, I take x minus 4 squared, and I should get 9. Now this one's a little bit tricky. It trips some of you up a little bit. But you'll notice that you take the square root of both sides, and when you do that, remember, you get x minus 4 equals plus or minus 3. You can't forget that when you take the square root. So that means I'm going to write two equations, one that's equal to a positive 3 and one that's equal to a negative 3. And so I have x minus 4 equals 3 and x minus 4 equals negative 3, which should give you two different answers, one of positive 7 and one of positive 1. I'm guessing that most of you came up with the first answer, but not the second one if you lost points. So make sure you remember that plus or minus part. And last but not least, again, we're having some problems with lettering on this test. This should be letter F, but it's our second letter D. And it says 3 to the x minus 2 power equals 27. I know that in order to equal 27, I have to have 3 to the 3rd power. And so that tells me that x minus 2 has to equal 3. Because I need to raise 3 to the 3rd power to get to 27. So in order for that to be true, in order for x minus 2 to equal 3, I have to have x equals 5 by adding 2 to both sides. A lot of little pieces, but nothing too complicated in that problem. Moving on, now we're talking about log transforms. So it gives you an example on the right of what the graph of y equals log base 3 of x minus 1 is. And so that graph takes our x-intercept that's normally at 1, 0 and shifts it 1 unit to the right. Okay, so using that, it asks what a possible equation of the graph below is. And so you'll notice that if you look at the locator point that normally started at 1, 0, it had to have shifted 2 units over to the left and then 1 unit down. Okay, so given that information, I can write my equation of this function using what we know about h and k in our transformations. Since we're talking about log base 3, one of your possible examples could be y equals log base 3 of x plus 2 minus 1. Alright, then we had that little typo in number 2 that should have been a log base 3, not log of 3x minus 1. But this equation tells me that I need to shift my log graph up 2, and I need to shift it over to the right 1, okay, which means that my locator point is going to be at positive 2, positive 2. Okay. Okay, the reason that it's not at positive 1, 2 is because our locator point on logarithms does not start at 0, 0, it starts at 1, 0. So you got to make sure that you account for that. Our asymptote also moves over from the y-axis. It also has to shift over 1 to the right with our locator point, and so I do that little asymptote in there as well. Make sure that's clear on your graph. Alright, and now we're talking about the back page of that test, which gets at some of the other standards that showed up in your homework or that you might have used on some other problems. And the first thing is composition functions. Remember that, sort of like order of operations, we always want to start on the inside, and so we'll start with figuring out what that f at 3 is, meaning I want to plug 3 into my function f of x, and when I do that I end up with 2 times 3 squared. Exponents come before multiplying, so it turns into 2 times 9, and then our f at 3 is 18. Now what I'm going to do is I'm going to take that 18 and I'm going to plug it in as my new input to g. Okay, so I take 18 and that's what I plug into my function g, and so I do g at 18 is 3 times 18 minus 5. You'll do 54 minus 5 equals 49. So that whole composition function, starting from the inside and working out, is g at f at 3 equals 49, okay, when we do both of those steps. And simplifying these fractions, the first one was a dividing problem, and remember that you always want to, when you're simplifying, you want to start factoring the tops and the bottoms of all of these, because you can only cross things out if they're separated by multiplication. You can't start crossing out things that are adding and subtracting each other. You can only divide things that on the top and the bottom that are multiplying. Okay, and so I factored the top, I factored an x out of the top, and I got x times x minus 2. And then on the bottom, if you want to factor using your box and your diamond or the quadratic formula or whatever way you like to do it, you'll end up with x minus 2 times x minus 2. Then we have to deal with that division in that second fraction. Remember that dividing by a fraction is the same thing as multiplying by the reciprocal. And so I'm going to take this original factored part and I'm going to multiply it by x minus 2 over 4x squared. So all I did was I flipped that second fraction, and now I'm multiplying instead of dividing. Okay? Now is when I can start crossing things out, because I have all these things that are multiplying each other. So I can cross out x minus 2 on the top and the bottom 2 times. I can get rid of the 1x on the top with one of my 2x's on the bottom, and I'm left with just 1 over 4x. In letter B, we are now subtracting, and remember that when you're adding or subtracting fractions, you have to get a common denominator. So whether I just have numbers in the bottom, or when I have expressions in the bottom denominators of my fractions, like in this problem, okay, you have to have the same thing. Now fortunately, we were nice, and we gave it to you with the same thing on the bottom already. So all you had to do was subtract what was on the top of your fractions. And so you can rewrite this as x minus 2. I just took those two numerators and subtracted them. And then I factored the denominator. So I factored it to be x minus 2 times x plus 1. And again, you can divide x minus 2 by x minus 2 and get 1. And that's why I can cross those two out with each other, because you can cross out the entire term, not just parts of it. Okay, so those are your two simplified fractions. And don't those look so much nicer than what we started with? Gotta love when things work out nicely. Alright, only 2 problems left. So this one asks us to solve the inequality. Remember, we take out that inequality symbol and put in an equal sign so we can find our boundary points. And so the first thing I'm going to do is divide both sides by negative 2. And I get the absolute value of x minus 2 equals 5. Now here's where you want to split up your absolute value. So either x minus 2 could be 5 or x minus 2 could be negative 5. And this should sort of be review for you. Then you want to solve both of those by adding 2 to both sides. And you get x equals 7 and x equals negative 3. Those are your 2 boundary points. So when I like to plot them on a number line so I can easily see what direction I'm shading. And so I'll do that now, and I put negative 3 and 7. They have to be open circles on my number line because it's just a less than, not a less than or equal to. And then what I'm going to do is I'm going to test 0 in my original inequality, so I know if I want to shade between those 2 points or outside of those 2 points. So when I plug 0 in, it turns out that that makes the inequality false. So I want to shade the region that does not have 0, and that'll be the 2 sides pointing out rather than in between. Now I can write my two inequalities that our x has to be less than -3 or x has to be greater than 7. Okay. And last problem, and then you're done making test corrections. And this problem asked us to take this equation y equals a times b to the x power plus k and solve it for a couple different variables. The first one was b, and so I just subtracted k from both sides in this step. And then I divided both sides by a to get to this step. And then I just took the x root of both sides. So I don't know what x is, but if it was b squared, I would take the square root. If it was b cubed, I would take the cubed root. Okay, and so I can just call this the xth root of both sides. Okay, now in part B, it asks us to solve for x, and I'm going to start that by doing the same kind of thing. I start with the same equation, and I can get myself to this point where I have b to the x power equals y minus k over a. If you forgot how I did that, look back at part A. And then I want to change this to log form so I can solve it for x. And so my final answer will be x equals log base b of y minus k over a. So that is the entire Chapter 6 test in 21 minutes and 8 seconds. Now you should be getting close to ready for that retake if you need it. Just make sure that you go do those practice tests and make sure you're ready before you come to us. Alright, thanks guys. Bye.